Hi, this is Stephen Ness, the CEO and founder of folding.ai, and I'd like to tell you about using artificial intelligence and intelligence augmentation for structural biology. So artificial intelligence we've all heard about, that's using new machine learning techniques, deep learning techniques to look at huge amounts of data. But intelligence augmentation is then using that AI and combining it with humans in a collaborative interface. So in my talk today, I'll just start with the motivation. Why are we interested in this? Why is this a cool topic? And why are we interested in it right now? Then I'll talk about what proteins are and how proteins work. Then I'll talk a little bit about structural biology, which shows the structure and function of these proteins and biological macromolecules. Then I'll tell you a little bit about CASP, the competition that has sparked this interest, and AlphaFold 2, which is the entry from DeepMind in CASP. But we'll get into that. Then I'll talk about using AI for structural biology and what people have done so far. And then I'll talk about a new avenue of making drugs using proteins and RNA, not small molecules. And finally, I'll talk about the folding AI platform. So our motivation is the new results of AlphaFold 2. And AlphaFold 2 comes from DeepMind. And DeepMind is a division of Alphabet or Google, and they're known for applying artificial intelligence deep learning techniques to a variety of games. So you probably have heard of AlphaZero, and that's a system that can win chess and also was famously one of the first ones to win Go. They applied that then to AlphaStar, and that's using deep learning for StarCraft 2. They recently applied that to AlphaFold 2, and AlphaFold 2 uses artificial intelligence to solve a grand challenge in biology we've been working on for a long time, at least 50 years. It's called the protein folding problem. Many magazines and internet sources reported on this as it's a huge change. Nature magazine said it'll change everything. And IEEE Spectrum said DeepMind's breakthrough demonstrates deep learning's potential to dramatically accelerate scientific discovery. And also in not just in those magazines, but also in the chemistry magazines, it was called the Holy Grail of chemistry, and that AlphaFold 2 had solved the protein folding problem. And in business as well, people are very interested in saying that proven computational AI is a game changer. So what are proteins? And if you notice on the right-hand side of the screen, we're showing a protein RNA complex, and it'll kind of build up slowly over time, and it's the spliceosome. So the first picture we saw in one of the first overview slides had just one part, and now we're seeing a little bit of RNA as well. The proteins are in red and yellow, and the RNA is the lines in gray in the middle there, the kind of thicker gray lines. So what are proteins? So we all know DNA, that's the instructions in our cells, and that's kind of what makes each organism unique. DNA is then transcribed into mRNA, and mRNA then produces the protein, and there's huge protein machines involved in each part of those, but the one that takes the mRNA to protein is the ribosome. And you can see down at the bottom that you have a protein chain being built up. So it's like a linear chain, just like DNA or RNA, but it folds up into a unique pattern. What do proteins do? Well, proteins do so many things in your cell, and in combination with RNA, provide all the huge machines in your cell that really provides for life. So one of the most important ones is enzyme catalysis. And chemical reactions, if they were to happen normally, would take a really long time. Catalysts, especially enzyme protein catalysts, take the reactions we need for life and make them go faster. Without that, life would not be possible. They're also responsible for motion. So when you're moving your arms, all of that is actually driven by protein machines. For all growth and maintenance of your body, so your whole body is constructed out of proteins. Large part of your body is made out of proteins. And when you get injured, proteins provide the things that fix your body, and also it's the structural material that fixes your body. That leads us into structure, so it provides the structure for the cytoskeleton in your cell, and that provides the shape of the cell, and it's very important. Also for messengers, so like insulin is a small protein, and it's used as a messenger to communicate between cells, but there's many, many more things that our proteins are important for. On the right-hand side, we're seeing another visualization of a protein. This is showing the surface of a protein, and this is a beta-lactamase, which is a enzyme that bacteria produce to become multi-drug resistant. So when you take a drug and the bacteria is resistant to it, this is one of the ways that the bacteria can do that, and it actually eats the drug. It chews up the drug, and shown in the stick figure is showing the drug, a drug in the active site. This is one of the structures that I was lucky to participate in for looking at antibiotic resistance. This is 1 ERM in the PDB. So now that we know about proteins, let's talk about the structural biology and what the structure of the proteins is. You can see on the right hand, the spliceosome is assembling itself more now. We're showing some more red proteins at the bottom. Those red kind of curly things are alpha helices, which are some of the important secondary structural elements of a protein. So what is structural biology? It's the study of the structure of macromolecules in the body, and that's mostly proteins and RNA. And the hypothesis is that if you look at the structure of a protein, that relates to its function, although that's actually challenging to figure out. We've determined many structures over the past 50, 60 years. There's over 170,000 structures now in something called the Protein Data Bank, which is an online electronic repository of all the proteins in the world. It actually used to not even be online. It was before things were online. And you used to send in your actual structure coordinates to them, but now it's all online. There's a number of techniques that you can use to solve the structures of proteins. The first one is X-ray crystallography, and that's one of the most important ones. It's shown on the right-hand side, and it's quite a complex process. You can make crystals out of proteins, and you've all seen salt crystals, right? Well, that's just a crystal of two different kinds of atoms, sodium and chlorine, and though that's like a small molecule crystal. Well, it's possible to take that huge protein that we were looking at before, and if you just tweak the conditions exactly right and try really hard, try many conditions, sometimes you can produce a crystal of a protein. It's quite challenging to do, but if you can make that crystal, then you can shoot it with X-rays. And those X-rays, if you collect the patterns of it, it'll have a pattern of dots. And you can see that down below the crystal where it says diffraction pattern. The positions of those dots, that just relates to the crystal lattice. So that just like the arrangement of the proteins, it's actually the intensities of those spots that shows you what the structure of the protein is. So the arrangement of the spots just shows you what the crystal lattice is, the symmetry is, but it's actually the intensities of the spots that's important. The intensity is important, but actually we're losing half the information when we collect that pattern. We're losing the phase information. So somehow we have to get the phase information out of that. And we use a variety of techniques. Things have improved a lot. You can use molecular replacement. So if you know approximately what your protein will look like, you can put an approximate version of it in there and then calculate what the electron density would be of your observed versus your calculated phases. So that's that experimental phasing. And eventually you get an electron density map, and you can fit a protein into that electron density map to get a final model structure. Another way of doing structure determination is with nuclear magnetic resonance, NMR, and a really exciting new one that's a lot easier because you don't have to make a crystal is cryo-EM, cryo-electron microscopy, and that's using electron microscopes, really specific ones, to look at the structures of the atoms in there. Cryo-EM is great, but it's it's not quite producing atomic level structures yet. It's getting there. But when that technique really is totally perfected, it's going to be a real revolution in collecting those structures. So that's exciting. So what's the protein folding problem? And it's hard to do those structure determination methods I was telling you about. X-ray crystallography is one of the most used ones, and sometimes it's impossible to make those crystals. Like on the right-hand side, we're seeing the structure of the ribosome, and it's a huge unit, huge set of different proteins and RNA put together, and it was really difficult to make crystals that would diffract to atomic resolution of the ribosome. So because it's so difficult, maybe we could fold a protein with a computer. Maybe if we just took the sequence of the RNA and DNA, we could figure out what a protein complex would look like, or if we just took the protein, what a single protein would look like. It's how a protein chains folds to a three-dimensional structure. There's a variety of different kinds of structures of a protein that we can look at. So the primary structure is just the sequence of amino acids in that polypeptide chain. So an amino acid is also known as a peptide, and a bunch of those together is a polypeptide chain. So we can get that a variety of ways, but usually we just sequence DNA. That's really easy nowadays. After that, then the protein also has a secondary structure. And that's kind of what we're seeing over on the right with the red and yellow. And there's a few different secondary structure elements. The most important are alpha helices, and those are shown in red on the right there. And those are this helical arrangement of the backbone, and it's like a spiral, and that's one of the stabilized elements. It's one of the building blocks of a protein. There's also beta sheets, and that's shown in yellow on the right, and that's arrangement where you have multiple parallel chains, polypeptide chains that come together, and then that's another kind of secondary structural element. Those two come together into the three-dimensional structure. So those secondary structure elements all come together into a three-dimensional structure. After that, there's the quaternary structure, and that's when you assemble multiple polypeptide chains together. So on the right is showing that quaternary structure where you have multiple proteins and RNA all coming together to make this huge protein machine. And shown on the right is the ribosome. And the ribosome is what takes the mRNA and actually makes a protein. So it's this huge protein machine that makes proteins. There's Levinthal's paradox. So if you have like an amino acid chain, like a protein of about 300 amino acids, there can be 10 to the 143 possible conformations of that peptide chain. So trying to find that one correct structure out of 10 to the 143 zeros after it is very challenging. So how do we fold a protein? Well, proteins are made of atoms, so really why don't we just simulate it all with quantum mechanics, because that's the way that we can represent atoms. Unfortunately, that's very expensive to do, and we can only do it for very small molecules. So the way that we're doing it now is using a top-down method called classical mechanics. So we're just approximate the protein and all the atoms in the protein as just balls and sticks that are connected together, and they have bond lengths and bond angles that we're trying to preserve. And at the top is shown like a simple equation that's just like one of the most naive equations for having a force field that'll be able to model a protein. And it shows the bonded forces, so it's like trying to keep the atoms the correct distance from each other, and the angles between those different atoms. The dihedrals is when you have 4 atoms and you rotate them around, there's certain positions that they want to be in more often. And then it's showing the unbonded forces, so it's showing the van der Waals forces at the front there and the electrostatic forces. This is a really simple equation, and it doesn't work so well in practice. So what people have been doing is taking more and more terms and adding more and more statistical terms to those equations to try to accurately represent proteins. And shown at the bottom is some of the force fields from Rosetta, which is a very popular set of packages for modeling proteins. And you can see there's quite a few different terms, and this does pretty good, but even this, if you just give it a random chain unfolded, it'll be unlikely to find the exact protein structure. So what people have been doing instead is they're using things like bottom-up methods, so like homology modeling, where you take similar proteins that already have their structures determined and see if you can determine your structure from that. Use that as the starting point. That's been used for many years now, and then recently people have been using machine learning and the huge amount of information we have to try to fold the protein. So now that we're talking about the protein folding problem, we can talk about CASP and AlphaFold 2. And CASP is the critical assessment of structure prediction, and it's not a contest, or it was not a contest. It's been held since 1994, and it's a whole bunch of teams coming together to try to predict the structures of proteins. There's a whole bunch of different categories in CASP, and one of them is ab initio folding. Ab initio folding is where you have like a protein, you don't have any analogs of the structure, you don't have anything you can do homology modeling with, and you're just trying to fold that. And that's the one that AlphaFold 2 won. On the right, you can see the results of the CASP, and this is just since CASP 7 in 2006. You can see that the results were actually slightly declining in 2012 and 2014. In 2016, it got a bit better, and then Google came in, AlphaFold came in 2018, and had significantly better performance than all the other competitors using deep learning. In just very recently in the CASP 2020, they completely rewrote the algorithm and got a whole new team together, just like an amazing team of at least 10 scientists, and most of them could have had their own research labs. These are very high-powered scientists, and they applied just millions of dollars, if not tens of millions or more, in computational resources and human resources in solving this problem. And they really basically solved the protein folding problem. They got 87% accuracy in CASP 14, and that's what all those results were for. On the right-hand side at the bottom, you can see the line at the very top is showing the target difficulty versus the score, this global distance test score. And you can see that the AlphaFold 2 just outperformed every other method just significantly, even on very tough proteins. The CASP 14 without DeepMind results is still high, and it's the line, the slightly curving line just below that one, but you can see that AlphaFold 2 just did much better. AlphaFold 2 only participated in one part of the CASP 2, ab initio folding. There's still the homology modeling and contact prediction and function prediction categories. So there's lots of more things to do, but they really did extremely well in ab initio folding. So just telling a little bit more about AlphaFold 2, they achieved 80% accuracy on the ab initio folding based on this global distance test score. They have a completely rewritten algorithm from the old AlphaFold 2, and we don't really know all the details. They've published a little bit on a blog post. It uses the transformer-based architecture, which is a new neural network-based architecture that's extremely powerful and was used for natural language processing and now is being applied to proteins. It also uses a huge amount of protein sequence data, so it's taking into account the fact that we have just tons of DNA that's been sequenced that we can turn into proteins, and that gives us just millions and millions of different protein primary structure that we can use. They probably use 3D structure information as well from that protein data bank, and it uses more than 170,000 different structures. And also they use some novel features that they have that they don't talk about too much. What's really interesting is that they use this agile and collaborative methodology. So it's using these ideas that we have in software, where it's this agile methodology where we all get together every day and discuss what's happening, have the stand-up, really collaborative. And they also used Rosetta for doing energy minimization. The transformer is a really exciting new neural network, or what some people are calling matrix network. And it was first developed for natural language processing. So they needed ways to translate human languages, and existing convolutional neural networks, LSTMs, RNNs, had limitations. So this is a way that we can hopefully overcome those. One of the most important parts of this transformer architecture is that you have an encoder. So shown on the right here, the encoder is on the left, and then you have a decoder, which is on the right. So you have these two different machine learning systems, and they basically kind of create a shared language, an intermediate language that they can communicate within. And that's shown by the connection between those. There's a few really important parts about the transformer architecture. One of the most important is attention. So there's both self-attention and multi-headed attention, and we'll have a whole video about that. But it's like how the different words in a sentence can have attention, or can know about other words in that sentence. So instead of just having like a small window that you can look at how one word would apply to the others, it's looking at all the words at once and seeing how each one is important. So for natural language processing, you could have things like one word might have different meanings in two contexts, but if you look at the whole context of the sentence, then you can determine that. So you can have self-attention and also multi-headed attention. And multi-headed attention is that self-attention, but on multiple layers. Another really important part of transformers, you have this positional encoding. So you can see down at the bottom, you have input embedding and then positional encoding. And that applies sine and cosines to the different positions of the letters. And that's kind of how you get that self-attention. You apply another mathematical function on top of the inputs to let the inputs have information about other parts of the structure. An important part is the layer normalization. So you can see that add and norm after the multi-headed attention. And that's, you're normalizing the layers and you're kind of getting different features out of those layers and turning that into a feature vector. And then another important part is at the end, you have this linear layer, which turns all those matrices into features, and then you can turn that into probabilities at the very end with a softmax layer. And again, we'd need like whole videos to describe that. There's some excellent videos on YouTube about that. So how can we apply those artificial intelligence things to structural biology? And AlphaFold 2 is one example. And there's a lot of other people that are looking at that. One is this great work for tasks assessing protein embeddings, or tape. And that came out of Berkeley and Facebook. And they came up with the BERT base model. And that's pre-trained on a masked language modeling of 31 million protein sequences. So they took just tons of protein sequences and then masked out one residue at a time and tried to predict what would happen at that residue. And they have a variety of different applications of that. One that was really interesting was in the Bertology Meets Biology paper, where they're visualizing those tape results. And they found that in those attention heads that we were talking about, that multi-head attention, that one of the attention heads predicted binding sites. Attention head 312 predicted where proteins were binding to one another. And that's shown here on the right. You're looking at the different amino acids that have the most attention. The attention vector is shown by the width of the orange lines, and it's showing the amino acids that are important in the contact between two proteins. So let's just take a little detour. Now we know about how to use AI. Now, why is this so interesting right now? Well, right now, to produce drugs, almost all drugs are small molecules. And that's because that's the way that we can get something into the cell. And on the right is shown a drug molecule in that beta-lactamase, that antibiotic resistance protein. And that small molecule is bound in the active site. It's actually, in this case, it's covalently linked in the active site. And the process of rational drug design is you determine a protein structure and then you try to find a small molecule that'll fit into that active site. And in a few cases, this has been extremely successful. Like the drugs we have to combat AIDS, like why AIDS isn't like a huge pandemic still, is these kind of drugs, that HIV drug cocktail. So those drugs were determined, their structures of the proteins were determined, and then drugs that would fit into those were produced, were like what drug would work was designed and produced, and that's what makes that HIV drug cocktail. And it's really, unfortunately, a very time-consuming and expensive process, so it's only been applied to a very few number of targets. AIDS, HIV was one of the most important ones. I was lucky to participate in a search for drugs for hepatitis C. So we're looking at different drug molecules of hepatitis C, and also for novel antibiotics. So on the right is showing some way that we're trying to design new drugs that could be new antibiotics that would stop multi-drug resistant bacteria. But there's a lot of problems with using small molecule drugs. They're great, and that's what almost all drugs are. But small molecules are difficult to model with force fields. they're quantum mechanical systems, and you're trying to model that quantum mechanical system with classical physics, and it's hard to do that. It's hard. You have to have a lot of different kind of hacks in your force field to try to like figure out what that drug molecule would look like. People have done great work with it, but it's very hard. It's also hard to find a small drug molecule that'll bind with high affinity to a protein. That's because the surface area of contact is pretty small, and the bigger the drug molecule is, often the more toxic it is, or the harder it is to get into a cell. So it's a real tough balancing act. And if it doesn't bind with high affinity, or if it binds with high affinity to another protein, then that can cause side effects. One of the most challenging things in terms of like actually making the new drugs in this kind of like rational drug design is that you actually need to get a chemist to make the molecule. So when I was working on projects with trying to do rational drug design, we'd come up with different candidates in the computer, but then we'd have to work with the chemists and see what kind of molecules could they actually produce. They'd give us those molecules and we'd soak them into the crystal structure and see if they'd work. But that would be like a 6-month process to like, or more, to go between like when you're actually simulating the system to actually when you can test it. One thing that's really interesting that just happened, and COVID-19 is a real tragedy, but it's really opened up the world to like a whole new paradigm. And mRNA, like we're talking about the start, it's a messenger RNA, and it produces the protein through the ribosome. But you can't just give someone mRNA and it'll make a protein. Because there's RNA viruses, our body has all these RNA aces, these molecules designed to eat up mRNA and RNA before it gets in your body. So you need some way to get it into the cell if you were to have some like mRNA delivery vehicle. And they, BioNTech and Moderna came up with lipid nanoparticles, and it's a way that you can get that mRNA right into a cell. So it's kind of like a Trojan horse. You can deliver your mRNA into the cell, and then the cell will just produce whatever protein that the mRNA codes for. That provides that protection from those nucleases, those RNA aces that are eating up the RNA. The first COVID vaccines, they actually just took days to develop. So if we were ready, we could just like develop these vaccines in no time and deliver them. We just had to obtain the DNA sequence of the virus, and that's easy. So all you have to do is just produce that mRNA, and we have ways to synthesize DNA and RNA really easily now. So it can be a really quick way to make some mRNA that'll make a protein in the cell. And then why now, instead of using small molecules, could we instead use proteins to interact in the cell? Like, you remember we were saying like a small drug molecule interacts with the active site? Well, what if you could get a whole other protein to just cover the entire active site? Like if there was that drug resistance beta-lactamase, why don't you get a protein just covers the entire face of the whole protein and just stops the whole thing from working? They can have a much larger surface area than the small molecule drugs, and that can lead to much higher binding affinity. And actually you see that in nature. This shown on the right is showing E. coli protein that'll bind to a protein in your cell, and evolution has made the E. coli protein just bind extremely tightly to that protein in your cell. So we can model that same process of evolution in the computer to try to optimize a protein structure exactly to fit another protein molecule. The tricky part is to make the algorithms that'll actually help us design those proteins. We can use proteins as the molecule to stick to another molecule, but we could also use RNA, and that gives us many more targets to interact with, and some really important targets for important things like cancer and aging. And RNA is present is present as complexes with proteins in some of the really most important things in the cell, like the ribosome we were talking about and the spliceosome. Shown over on the right is the spliceosome, and that's an important big protein machine that takes the mRNA that comes out of the nucleus, or like comes out, that's produced from the DNA, and then takes out introns out of that, takes out the non-coding regions out of it. And it's involved in a number of diseases, and it's a really important system. So now I just want to tell you a little bit about the Folding AI platform. And we're interested in making a platform that provides artificial intelligence, but also intelligence augmentation to these problems. And in some cases, just like traditional AI, where you just dump a lot of data at a problem, like the things that are being done by OpenAI, Google, Facebook, where you just take a ton of data and apply it. That's reaching some limits, and you can even see with AlphaFold 2 the 87% limit. In a lot of cases, if you just have more careful selection of the data and visualization, maybe you'll be able to find the outliers in your data, the problematic data, and remove that and really model your data better. And there's a lot of examples of that. One, when I was working at Google Research, interning at Google Research, they thought some of the data was sparse, but it turned out if you've just visualized it quickly that the data wasn't actually sparse, and that was causing problems with their machine learning methods. As soon as we could see that data, that it wasn't sparse, we could do transformations on the data to make it sparse, and then the machine learning could work a lot better. Also, for proteins and RNA, there's a lot of specialized knowledge that scientists have, and how can we exploit this knowledge? We use a system of computer-supported collaborative work, and this is a way that we can have design systems to have people work with other people and work with AIs together. Our system, our platform, looks kind of like this. We have the data sources on the left. So you have the data lake with all your data. You have the protein sequence data, homology data, data from the protein data bank, and also proprietary data from a company. That all feeds into our AI engine, and then we predict a protein structure out of that. Now, one thing I've really seen a lot when I was doing rational drug design is it's really important to get feedback, experimental feedback, because if you're just simulating things, there's so many ways that the simulation can go wrong. So an important part of our system is that after you predict that protein structure, you actually produce the protein and determine its structure, either by X-ray crystallography or cryo-EM, and that feeds back into the AI engine. There's also the interactive interface. So you'll produce that predicted protein structure, and then you can have multiple people come together, work in an interactive interface to try to find the right data to feed into the AI engine. And when I was working on the hepatitis C problem, it's really interesting that there is like I was the one who was doing the molecular modeling, but then there is the PIs. They'd stand behind me and say, oh, try this, try this. They're the ones with all the great knowledge, all the scientific knowledge. But then there's people that are like the gamers who know how to actually move the molecules on the screen. And it's that collaboration between them that makes it really powerful. And thank you for listening to the talk. Our website is at folding.ai, and please email us at ai@folding.ai. Some great papers is the Bertology Meets Biology paper. That's our first product. We're delivering a visualization of that in different software packages, including Mo. That gets data from that tape paper, the Evaluating Protein Transfer Learning with Tape, by Rochenreau et al. And then the Attention is All You Need is the start of the transformer That was one of the first transformer papers, or the paper that described transformers from Google. That's an excellent paper to look at. And then finally, there's the blog post from DeepMind talking about AlphaFold 2 and how it's a solution to the 50-year-old grand challenge. Thank you very much. Again, I'm Stephen Ness from folding.ai, and we're developing a platform for intelligence augmentation and artificial intelligence for protein docking, protein folding.